Hello everyone, my name is Michael Vega along with Yevgen Barsukov. Today we'll be talking about MaxLifeTechnolgy and how it extends battery service life and minimizes charge time. In the agenda for today, we'll be solving the challenge of fast charging, also talking about battery degradation and what factors impact battery degradation. We'll be talking about the multi-level charging optimize, which uses a battery modeling framework. And also we'll talk about the multi-level charging ecosystem. Two main points that come to mind with battery power systems today is how long will I actually run my system with battery power? And also we're interested in how long will it actually take to charge my battery? Everyone wants to charge fast, but the question is, should we really be able to charge fast? Charging fast is so easy, as easy as just using high charge currents which are greater than 1 C rate. However, it's undesirable to use over 1 C rate of charge current for given batteries because it can impact the life cycle and the lifetime of a lithium-ion battery. But we still want to charge fast because with today's dependencies on mobile computing devices for our daily lives, it's been very important that we count on the battery capacity for our devices and be able to replenish these as soon as possible when the battery is depleted. Today we'll talk about MaxLifeTechnolgy, which combines the voltage and temperature modeling with degradation modeling to find charge profile with globally minimized degradation for any given temperature and reduce charge time. I'll now leave you with Yevgen Barsukov so that he could talk about battery degradation.
In order to optimize the battery charging for the fastest charge time that would not cause additional degradation, we first need to understand the causes of degradation, and we need to have ability to model degradation. So it is well known that when battery is aging, there is two things that happens from the point of view of its functionality. Its impedance is increasing, and you can see on the left upper graph impedance spectra that are recorded during 100 cycles of battery aging. You can see that the high frequency part of the spectrum on the left is not changing between the cycles, but the low frequency part of the spectrum on the right is increasing about 70% in just 100 cycles. So that would affect the usable capacity of the battery if you use it at a high rate applications. But if you use it at a low rate, the capacity will barely change because the IR drop will be still small because I is small. So we can use this effect to investigate the chemical capacity of the battery, and that is done at the left bottom figure here. It shows the discharge profiles at a low rate, at C over 10, basically 10-hour discharge rate, also over 100 cycles, and you can see that during the same period the chemical capacity only decreases by about 6%. So you can see that the major effect is the impedance increase, while the chemical capacity change is present but not as big. So what are the reasons for these effects? First, we need to have a quick look at the insides of the battery to understand the structure of its electrodes. So pretty much for all lithium-ion batteries, the both anode and cathode would be a current collector and particles of active material that are kind of piled up and compressed. You can think about it kind of like an asphalt. So it has some solid particles which is held together by the binder, and there's also some conductive additive. So electron has to go all the way from current collector between the particles and conductive additive, and finally it reaches a particular particle. On the other side, the lithium ion has to go from the electrolyte solution between the particles in the pores, also until it reaches the surface of particular particle. Now let's have a close-up on a particular particle itself. The most important part in lithium-ion battery is the passivating layer on the surface of the particle. Lithium is extremely aggressive metal, and for example, if you drop a piece in water, it will explode or catch fire. For this reason, organic electrolytes are used for lithium-ion batteries. But even with organic electrolytes, lithium is still reacting. So the reason why lithium-ion battery is possible is that that reaction causes the passivating layer to grow on the particle surface, which eventually stops the access for the solvent molecules to the surface of the particle. But the lithium ions can still go through it. Unfortunately, this layer is not 100% unpenetrable for the solvent, and that is the main reason for degradation. So the irreversible reaction on the material surface continues even if battery is not used. Even if it's just stored in charged state, it will degrade. And that growth of passivating layer will cause a loss of electric contact between particles. So some of the particles will be just lost eventually. So that will cause a capacity to decrease. And also loss of lithium itself. Lithium is getting used up when passivating layer is growing. So loss of lithium will also decrease the capacity. And impedance will increase because of the loss of electronic contact will increase impedance. Also the diffusion resistance across the passivating layer is going to increase, which also increases the impedance for the discharge. We lose the lithium, and some of the pores are also going to be blocked, which will increase the resistance of lithium transfer, which also adds up to the total resistance inside the battery. So this is the most important mechanism if you just store the battery. But if you are using the battery as it's supposed to be used, basically charging and discharging, some additional degradation effect comes in. And that happens because the particle, when it is charged and discharged, is expanding and contracting. A different material expand and contract by different amount. So graphite is actually pretty good in that sense. It only expands by 10%. But even then, it is enough to crack the passivating layer, because passivating layer is very brittle. It's not some solid ceramic material. It's kind of very brittle amorphous layer like chalk. But graphite is extremely strong, mechanically strong material, so it definitely cracks this layer very easily. And so anytime when you charge and discharge the battery, these cracks result in immediate contact between solvent and the surface of the particle, and the immediate reaction that forms some more of the passivating layer to block the access. And that uses up some amount of lithium every time you charge and discharge the battery. So you can think about that there is a storage degradation that if you don't cycle it, and plus there is a completely different mechanism when you charge and discharge the battery due to this particle cracking of the surface layer. There are some additional effects if battery is operated outside of its operation range. For example, if you over discharge it, you could dissolve active material or corrode the current collectors. And if you charge it too fast, you can have lithium plating. So I will talk about it in more detail because it's a very important mechanism. So the first, to summarize what are the important factors that speed up the degradation, it is voltage. So if you don't have any lithium in the system, your voltage will be low, and so you will not have any degradation. That high temperature speeds up both the diffusion and chemical reactions, so for that reason degradation is increasing with temperature. And the fast charge, of course, causes the cracking of the passivating layer, and so it is only affecting the cycling degradation. And lithium plating would occur at low temperatures or very high rates of discharge. And there is only one factor that decreases degradation, that is the time that is passed, because when the passivating layer is growing, it is more difficult to diffuse through it for the solvent, and so it slows down the degradation rate. So in order to model degradation, we model the both storage and cycling degradation separately. First, we can obtain the storage degradation data from the cell manufacturers. That kind of data looks like this. Battery is stored, for example, at a fixed voltage, for example 4.1 volt, and at 20 degrees C, and periodically discharged, say once a month. This way you can observe the trend how the capacity is decreasing even though you're not cycling the battery. You can see that at 4.1 volt the degradation would be the smallest. At 4.2 volt it gets bigger. It's about twice higher, and especially drastically increase you can see at 60 degrees C. In this case degradation goes 4 times bigger than it was at 20 degrees C. So we are fitting all this data to get the parameters of our degradation model, and that can be either used generically for the typical lithium cobalt oxide cells, or it can be optimized for any particular cell. So once we have this static degradation model, we can now take the cycling degradation data. For example, if you run a cycling test for 500 cycles, you will obtain this kind of degradation versus cycle number graph. But also the data will be collected for actual voltage, temperature, and current during this test. We can take this data and apply our time-based degradation model to this data to find out how much time-based degradation happened at that time. And then we take the total degradation and subtract the time-based degradation from it, and the rest will be the degradation due to cycling. So basically the cracking degradation. So we can calculate the charge acceleration factor and add it to our model. So now we can model both cycling degradation and time-based degradation. So when we applied this normal operation mode, the degradation model, to degradation at a very high charge rates, the expectation was that we will be able to predict this increased degradation, because the overall idea in the industry was that this increased degradation happens because of higher temperature. And indeed, there will be a higher temperature if we charge at a faster rate, because there are more I²R heating. But when we apply the degradation model, we have seen the degradation increases only by a few %, because the temperature change is really not that big. But the experimental data is showing that if you go from the recommended charging rate 1C just a little bit higher to 1.2C rate, your cycle life until you lose 20% capacity is changing from 500 cycles, which is kind of industry standard, to about 250 cycles. You're losing half of your cycle life just because of the increase of rate by 20%. And if you increase it to 1.4C, in this case, you will lose 20% in about 100 cycles. So this is 5 times less cycle life. So why such drastic effect? Well, there is already known in the industry that when you charge battery at low temperatures, there is such effect as lithium plating. Lithium plating is always competing with the lithium intercalation for the direction where lithium will go. You can think about it as that the lithium intercalation is a resistor, and the lithium plating kind of is a Zener diode that is put in parallel with that resistor. So once you reach certain, so the Zener will not conduct before you reach certain IR drop across this resistor. But once you reach this IR drop, it starts conducting, so most of the lithium will actually go into plating rather than into diffusion. To achieve this high IR drop, in the past, the most easy way to achieve it was at low temperature, because resistance, diffusion slows down a lot at low temperature, and so your diffusion resistance for intercalation is going to be huge at minus 20 degrees C. So you can deposit so much lithium that you will literally see it if you open the cell. It will be a silvery layer instead of a golden layer of intercalated lithium. And if you discharge the cell, you will see a higher voltage in the beginning, because voltage of lithium is smaller compared to voltage of intercalated lithium, and since the anode voltage is subtracted from overall cell voltage, your overall cell voltage is higher in that region. And that compared to the normal discharge voltage, you see there is a pretty big difference here. The same effect can also happen at room temperature. It is just more difficult to observe, because it is just the IR drop that you need to achieve. So you can do it either by having higher R, or you can do it by having the higher current. And that's what happens if you try to charge the lithium-ion battery faster as a recommended rate. You reach the critical threshold, and then the Zener diode has to start conducting, and you have some lithium deposition. And that causes a drastic additional degradation, because once lithium is deposited at room temperature, it will not just stay there. It will very quickly react with the solvent and again build more passivating layer, and lithium will be lost out of the system. And resistance will increase again because of passivating layer higher resistance. So this effect have been investigated in the literature, for example, in this paper by Aurora. And what they found is that this IR drop across the intercalation is very strongly dependent on the particle size of our active material. And that is kind of obvious because diffusion, even if diffusion coefficient is the same, the diffusion resistance is going to be inversely proportional to the particle size. So you have to diffuse through a thinner layer, basically, and in this case, your overall resistance will be less. And that has a very strong effect at the current when you will start lithium plating. So if you have a very small particles, like in the power tool batteries, you will not have any plating all the way to 6 milliampere-hour per square centimeter, which kind of corresponds to 3C rate. But if you go to the smaller, bigger particles, which happens if you go to notebook cells, for example, you want to have a higher energy density. So you're making compromise towards having higher energy density, but at the cost of having a higher resistance of your intercalation. So in this case, the plating already starts at much lower C rates. And finally, if we go to cell phones and even worse, the tablets, you can have up to 55 micron particle size. In this case, this is done to completely maximize the energy density, because you can pack much more material. Packing density is higher if you have a larger particle size. But that is at the cost at starting your lithium plating at the rate even as low as 0.5 C. So what it means is that we cannot just have one size-fit-all model for lithium plating. We have to have a model that is adjusted for different battery types. So to obtain this kind of model, we use the characterization data that we already collect for the purpose of our impedance track gauging system. And since we have to support 80% of all notebook battery systems and close to the same percent for cell phone and tablet systems, we have a huge database of what we call the chemical ID database for different cells. So this kind of discharge relaxation profile test allows us to collect both the static data, like open circuit voltage and low frequency resistance for different state of charge, but also dynamic data, such as impedance spectra over wide frequency range. And using this impedance spectra, we can derive the resistance effects on lithium plating. So this could be done when you go from so impedance spectrum contains effects of various processes. You can see here, depending on the frequency you're looking at, it will correspond to passivating layer or the electrochemical reaction, diffusion, and other low frequency processes. So from this spectrum, we can go to the physical model, and that physical model allows us to get the parameters that corresponds to each process, which we then plug in into nonlinear circuit model, which also contains lithium plating as one of the components. So now we can find this compromise between the diffusion, flow through the diffusion and flow through the lithium plating, and find how much lithium plating will happen at the different rates and conditions. So applying this to modeling of charge allows us to detect when the various degradation effects happen. So let's look at the comparison between the normal charge rate case and the high charge rate case. So in the normal charge rate, it is 0.6 C rate, that is close to recommended rate. The charge takes about 2 hours, and the current is lower. But the temperature is also staying kind of around 33 C. And if you look at the differential degradation, it is pretty much smooth. So there is no particular sharp features in the degradation profile. But if you go to the high rate charging at 1.2 C rate, the current is obviously much higher, and the charge is finished in about 1.3 hours. Temperature increase is present also, but it's not that big. It's just about 3 degrees C. So if you don't consider lithium plating, that just the temperature increase itself will not cause too much of additional degradation. So there is some additional degradation, but if you look at the integral degradation over the entire charge cycle, the comparison with the low rate difference is pretty small, just a couple of percent. But if you consider lithium plating, you can see that it occurs in a pretty narrow range here, where our voltage is already high, so we're coming pretty close already to this trigger threshold for the lithium plating, and this just some small additional IR drop causes us to go over the threshold. Even though the area where it occurs is pretty narrow, when you integrate it and look at the overall degradation in charge, you can see that it results in a huge difference in the degradation in one cycle. It's more than double the degradation. Even though this is just a new battery effect, when battery ages, the degradation kind of slows down. But even for aged battery, the effect is usually around 30%, which is pretty high degradation effect. So here is how it affects the long-term cycling. So if you look at just the storage degradation, that would be this green line. And if you look at storage degradation plus cycling degradation, that would be this purple line. But this excludes lithium plating. So if you add the lithium plating effect to it, then our modeling coincides very close with experimental data for this 1.2C rate cycling. So now we can see that we can model it pretty well, but what can we do to eliminate this effect? Well, to eliminate this effect, we can combine our voltage and temperature modeling with degradation modeling and run an optimization that allows us to find the charge profile that will result in the shortest possible charge time, or whatever predefined charge time we can ask, while minimizing the degradation. We applied this to 5-level CCCV charge profile, which is supported by our BQ-BMU, but it could be applied to any other charge control optimization as well. So let's look what it did for 5-level CCCV. So here is a comparison of the 1.2C charge rate case that we were discussing earlier. You can see here there's about 1.3 hour charging, constant current and then constant voltage. That is the case where we had a high degradation. And the optimized profile results in about the same charge time. But it has some significant differences. So first of all, at the beginning, the current is higher. And it's important to understand that to achieve the same charge time as CCCV, you do need to have a higher current rate, because CCCV is theoretically fastest possible charge method if you have a certain current limit. So we have to exceed this current limit for some period of the charge in order to achieve the same charge time. And in this case, the optimizer chose to exceed this current limit at the beginning because degradation is lower at the beginning, and also but it avoided the area where we had most of the lithium plating here, close to this transition between the CC to CV mode. And as overall, this profile results in the same charge time, but as you can see, if in the differential degradation, now this big spike due to the lithium plating has disappeared. And correspondingly, the integral degradation of this case for optimized MLC profile is almost the same as it was for the case without lithium plating. And that can be observed also for the cycling case. So here is the normal CCCV cycling. So time-based degradation remains the same between CCCV and MLC. But the cycling degradation, that's where you see a big effect. So the green line corresponds to the case without lithium plating in the modeling, where we basically turn it off. And the red case with lithium plating. But with MLC, it doesn't matter if you actually turn on or turn off the lithium plating, because the profile itself eliminates it. So you can see that the cycling degradation data coincides with the same as without lithium plating. And we performed the testing of this protocol using our EVM, and we'll talk later about the hardware support for this. As you can see is that here is the experimental data for CCCV 1.2C rate fast charging, basically 1.5 hour. And the pink line was the modeling, But here is the experimental data. So the pink dots here corresponds to the actual experimental data on MLC profile for 1.5-hour case. And you can see that it very closely coincides with the theoretical prediction that was done actually long before the test was performed. And that test has continued after that for another over 600 cycles. And you can see that with CCCV fast charge case, the battery died after 450 cycles. So battery is considered dead when you lose 20% capacity. But with for the MLC case, the cycling continued and reached over 600 cycles. So that corresponds to about 40% increase in the cycle life, down to 80% capacity. And we will continue testing it until it goes to 30% drop in capacity, because that is also a useful test case. So you can see that basically you're getting something for nothing. You're getting a very fast charge time, but practically no additional degradation. So now Michael Vega is going to talk about the hardware implementation of this MaxLife technology.
Thank you, Yevgen. So now that we have a better understanding of MaxLife and battery degradation, let's talk about how we can make use of MaxLife. So Texas Instruments is very experienced with charger devices and battery gas gauge devices. So we figured, what better way to make use of MaxLife than using a technology that combines the use of a gas gauge and also the charger. So that will leave us to a battery management system, or BMU, which can help achieve shorter design times and to go to production quicker, and also improve savings in board component costs. Also, we can leverage the impedance track technology to achieve longer run times for batteries, and also have better charge termination accuracies and also recharge thresholds. And by making the gas gauge the brains of the BMU, we can be able to make use of the MaxLife, have charge control based on state of health, and also charge control based on temperature. The MaxLife ecosystem is not much different than today's solutions. So it still requires a battery adapter or AC adapter. Within the device, it's going to require, the system is going to require a charger IC, and in most cases a gas gauge. And all this is going to be powered from a battery. So the thing is, to make use of MaxLife, we have a quick setup on how to select, let's say, a combination of a charger and a gas gauge that will act as the BMU system, and based on what battery capacity and adapters. So today the system designers are already going to know what battery capacity they're going to use in their system, so that they can try to achieve a given or desired runtime for their system. So once you determine the actual battery capacity for that system, then to make the best use or the most use of MaxLife, we have here different combinations of chargers and gas gauge. So for battery capacities less than 1670 milliamp hours, we have the BQ24250 family of chargers that could be used with the 27532 G1 gas gauges. And this will require a 10-watt adapter, so you can make use of MaxLife. And you can see with the other battery capacity thresholds, we have available the BQ24160X charger family that is used with the BQ27530. And we have, for the larger battery capacities, the BQ2419X, which is used with the BQ27531 gas gauge. And you can see for any of these combinations what adapter ratings are necessary to make use of MaxLife. Here's an example of what the circuitry will look like for a BMU system. In this case, for example, we got our BQ2419X family charger and the BQ27530X. So the APU or application processor will communicate over I2C with the gas gauge. while the gas gauge will own all the gauging algorithm by measuring voltage, temperature, and the current that leaves or enters the battery, and be able to determine what the state of charge and state of health for that battery is. Based on that information, it will also make decision to run the MaxLife algorithm and directly charge the take control of the battery charger. So preparing for MaxLife, now that you've been able to design the circuit, select your components appropriately, going into production with MaxLife becomes as easy as using the current process for using the battery chemistry IDs into production. So now the MaxLife parameters become part of the ChemID process. So customers can select, what the charge current available is going to be based on the BMU selection guide, and then once the ChemID is determined, the MaxLife parameters actually become part of the configuration for optimized fast charging. So to conclude this presentation, we want to highlight some points to take away from today's presentation. So we want to make sure you know that today's technology available by TI, MaxLifeTechnolgy, combines voltage and temperature modeling with a degradation model that actually will find a charge profile that will globally minimize degradation for any given temperature and a required charge time. Also, we can make use of the largest database that's available today for battery chemical parameters, and TI has this with the longest database available for ChemIDs. And also, we want to highlight that lithium plating, which is an important degradation factor, comes into effect especially at very high charge rates. So with the multi-level charging profile, you can optimize lithium plating considerations so that it reduces the degradation that can happen up to 25% in a case where you're trying to charge at 1.5 hour charge time. And because of the impedance track, we're able to update the algorithm throughout the life of the application so that the MaxLife parameters actually are adjusted as the battery ages with the use of the system throughout its life. And with today's portfolio, TI has devices that can allow charge currents up to 4.5 amps while allowing our MaxLife algorithm. Well, we appreciate your time today, and we hope that you learned something about MaxLife technology with Texas Instruments.